So now we're ready to introduce at least a simple way to do implicit finite divided difference for the parabolic PDE. And again, we're just going to rewrite our heat equation, well, maybe you don't call it heat equation. This is our partial differential equation that we're trying to solve. K, second partial of t with respect to x, is equal to dt d, found a typo here, with respect to time. So we're looking at the transient solution to this parabolic differential equation and what we had done. And so this is all, can't draw a curly brace right now. This is all the explicit approach. So this is just a reminder, because we're going to contrast with the implicit approach. So we did second partial of t with respect to x is equal to, is this approximation, ti plus 1 L minus 2 ti L plus ti minus 1 L all over delta x squared. So this is what we're doing, and if we look here, it's this L up here. This is our time at our time point L. All right, and then we plugged these both into here, and that's what we got. Well, how are we going to do the implicit? Well, what we can do, and I'm just going to copy and paste this because that's going to be easier, is we can take, and instead of L, here we see it, instead of L, and I'm going to switch colors so it makes it more obvious what I'm doing here. Instead of L, let's use L plus 1. L plus 1, L plus 1. So we're going to use the L plus 1 points in this approximation, and then this is our implicit. That's what we do. That's it. That's all. This is just a simple implicit approach. And the other thing that's nice to do is look at the computational elements. And I'm gonna move this down here. Let's just get that out of the way. Is to look at the computational elements. Let me draw those, and then I'll come back and explain them. All right, so I drew at least the frames for the computational elements here, and what we're going to look at is we're going to look at what points this explicit method uses. So if we look, and this is so we have the ti plus 1 L. So if we go to the coordinates, and let's use an x for the t's and an O for these. So let's use an O for these and an X for these. So Ti plus 1L, so Ti plus 1L, so that's this point. We use Ti to the L, so we use this point. Ti minus 1L, so we use this point. Okay, now let's look at the second of the equation. We use Ti L plus 1. So L plus 1, we use this one, and we use TIL. We use this one. All right. So then that comes from this equation. So this is what a computational element is. And this is just the visualization of what we're using to compute our next point. Now here in the implicit approach, let's look. We're using Ti plus 1 L, Ti L plus 1, Ti minus 1 L plus 1. In other words, these three circles that we had here are now up here, and the x's are in the same place because we haven't done anything different here. They came from here. Again, so this is the visualization. So the visualization is we're using the value at this point to compute the next point, and this only appears in the time equation that we use this point here, and in space we're using all of these points. And the advantage that offers us is that it's both stable and convergent. So the implicit is stable and convergent without putting a stipulation on our step size. So we don't have to make any special considerations for our step size, and that is very nice because we may need to use a larger step size. We may not be able to make it that small. And so the great thing about this, both stable and convergent, regardless. I mean, it still has to be small enough, but that's the case. The other thing is that we haven't actually looked at the implicit method, what these equations end up looking like. Well, It turns out that if we write out all these equations, we can't just solve for the next point given the current time point. For each point in time, it ends up being a tridiagonal system of equations that we have to solve. However, we can solve a tridiagonal system. You basically have to, well, not invert, but solve a system with a tridiagonal matrix. Well, you can remember maybe Thomas's algorithm that we learned before, which is an extremely efficient method to solve a tridiagonal system. So we have to do that in each step. So there is, so it is good, but it's not as good as it might seem because what we gain in being able to use a larger step size, we sort of lose in having to do more computations and actually having to invert a matrix or at least solve a full system of equations at each step.